So I'm going to talk about where we are at the moment in terms of current releases of Java, and then where we're going in terms of the future of Java. What's coming, what can you expect, and how are things changing? Because this is something that's quite important in terms of the way that you get access to the JDK, and more importantly, how you get access to the updates to the JDK. And we'll discuss that in terms of what's actually happening and what this will mean to you as developers and people using Java. Then the second half of the presentation, I'm going to talk about how you can make a better JVM, because that's what us all do as part of their business. Now, I'm not here to be a salesman, I'm not here to do marketing. I am going to tell you all about the technology so that you can judge for yourself whether you think it's worth having a look at and thinking about maybe using it. Because Java's a wonderful programming language. We all know that, and we love Java. But when it comes to using the JVM, the way the JVM works can sometimes have an impact on how well your application performs. I'm going to explore exactly how that works and what we can do to change the way it works, to improve it. So that's the idea of the presentation. So let's start with Java now. Where are we at the moment? And actually what I'm going to do is I'm going to start with what is now, a little bit of history, because this is not the current release. Was, but isn't anymore. So JDK 9. JDK 9 came out in September of last year. And it was a release which had been, say, hotly anticipated. People had been looking forward to JDK 9 for some time. There were lots of new features in JDK 9, and this is a list of them. I think there's about 87, I think I counted them all up. There's about 87 new features that made it into JDK 9. Many of them are quite small, some of them are more big, and of course there is one that is very big. And the one that's very big is the one that caused some problems in terms of delaying JDK 9, because Oracle and the Open JDK project wanted to make sure that they tried to avoid as many problems as possible with the implementation of the module system. So let's talk a little bit about what the platform module system actually is. It's all about taking the JDK and making it more manageable. Now, the reason for this is that if you go back in the history of Java, go all the way back to JDK 1.0. So let's quick show of hands. Anybody here used JDK 1.0? Okay, 1, 2, yes. You were going to say yes. So a couple of people who are as old as me and can remember JDK 1.0. If you look at the class libraries in JDK 1.0, you will find there are just over 200 classes that you can use for writing your applications. Now that's nice, you've got some libraries and you can do things with that, but it's not a very powerful or rich set of libraries. Over the last 23 years, more and more classes and methods have been added to Java. If you look at JDK 8, there are about 4,500 classes in the standard libraries, which is great, because now we don't have to write a list interface. We don't have to write a semaphore class. We don't have to write a string builder. All of these things are there for us. So this is great. But the problem is that all of these classes have been added to one file. Actually, it's two really, but one file, rt.jar. And so we've got this situation where we've got a monolithic set of libraries. As we know from the way that everybody's developing microservices now, monolithic is bad. We want to break it up into smaller pieces. And that's what a large part of the Java platform module system is about. Taking those libraries and breaking them up into more manageable chunks. The reason for that is quite a lot of reasons, but primarily it's about making it easier to maintain, easier to avoid security issues, and also for deployment. We now, as I said, have microservices as a very popular way of developing applications. In order to deploy a Java microservice, what we don't want to do is to have to deploy all 4,500 classes with our microservice. With the module system, we can now deploy just the modules that we need for that microservice. Make it smaller, more compact, much easier to deploy and so on. So we end up with 97 modules. There are 28 for Java SE, which is the Java standard. In the Oracle JDK, there's also Java FX, there's 8 of those. And there are 59 which are JDK-specific modules. These relate to things like tools, like JShell, various sort of things like that. There's one for Nashorn, so if you're using the scripting engine, there's a module for that. So there's lots of different things there. There's a second side to modularity. And this was one of the goals that the developers of modularity had, which was not just to break up the public APIs into manageable chunks, but also to encapsulate the internal APIs. There are 4,500 public APIs in rt.jar, but there's actually more classes there, because there are a lot of classes which are required to make the public ones work. And the most famous of those, or infamous, is sun, misc, unsafe. I really like sun, misc, unsafe because the clue is in the name, unsafe. You're not supposed to use it. The designers of Java never intended average developers to use that class. It allows you to do things which are dangerous. Dangerous in the terms of Java. So it's very easy using unsafe to crash your JVM. So they don't like you trying to use that. Now, the original idea had been to encapsulate all of those APIs, all of the private APIs. But the problem was that too many people had used things like sun, misc, unsafe. Has anybody ever used sun, misc, unsafe here? Nobody. Okay, very good. You have done very well. You have followed the instructions. But unfortunately, lots of people have. And so if I asked, does anybody here use a third-party library or framework like Spring or Log4j, anything like that? Yes. So you've used sun, misc, unsafe. You just don't know it, because a lot of people who write these frameworks have used sun, misc, unsafe. So Oracle and the OpenJDK decided that rather than encapsulating everything, they would still allow people access to them, but you would use special command line options so that you could make your code work. It wouldn't break backwards compatibility. That was very important. Related to modules is the idea of creating a runtime specifically for your application. And this comes back to the idea of microservices. If you want a runtime that only includes the modules for your application, your service, then JLink will do that for you. What it does is it takes a set of command line parameters and then it generates a directory structure that looks just like the JDK, has the same subdirectories, and can be used to run an application. So in this very simple example here, what we're doing is we're saying JLink from the JDK modules, add only the java.base module. You have to have java.base in every application, and output it to a directory called myimage. And if you look in that directory, you'll find there's a bin directory, a conf directory, a lib directory, just as there are in the JDK. And if you go into the bin directory, you'll find there's Java. If you run Java and you say list modules, you will see java.base. So that's the way it works. If you look at a slightly more realistic example, what I'm doing here is I've created an application that uses modules. And I can use JLink again, and I can say, use the JDK modules, use my modules, and add the main entry point module for my application. So I don't have to list out all the modules myself. The JLink command with the compiler will work out what's needed. So I simply say, comments all that, and output to my image. If I run Java again with list modules, I'll now see I've got java.base, I've got java.logging, java.sql, java.xml, comments all that, Zoop, and Zeta. So all of the modules I need to run my application are there, and I can use it. So this is a very powerful thing in terms of the module system. The next thing we need to consider is how JDK 9 impacts on compatibility. One of the decisions that was made by the developers of JDK 9 was that they were going to start making a change to Java, and a change in the sense of how they would maintain backwards compatibility. This is a quote directly from one of the product managers of Java at Oracle, and he said, "Clean applications that just depend on Java SE should just work." Now, I don't know about you, but I would rather see will just work, because that's a bit more sort of concrete. But the idea is that they should just work. And there are a few reasons why applications that work on JDK 8 won't work straight away on JDK 9. Modularity is one of those. If you've used things like sun, misc, unsafe, you may need to add some command line flags to make the APIs accessible to you. But there are some other things. There are some missing modules in JDK 9. The way that this was stated is very precise. It says, clean applications that only use java.se. Now, java.se is a module in JDK 9. In fact, it's what's called an aggregator module. That's a module that doesn't include any packages, but only includes references to other modules. So java.se is all the standard modules, java.base, java.login, java.xml, and so on. All the ones that make up the Java SE standard. Now, there is another aggregator module that's bizarrely and somewhat confusingly called java.se.ee. This is the enterprise edition side of standard edition Java. A number of classes and packages were added to Java over the years, which really shouldn't have been. And when I say they shouldn't have been added to Java SE, because they really kind of extended it beyond just the basic platform and started encroaching on the enterprise edition space. What the OpenJDK developers have said is that in JDK 9, anything which is included in the java.se.ee aggregator module will not be included by default for either compilation or runtime. That means that if you've used any of those APIs, when you try to run your application on JDK 9, even though it's being compiled on JDK 8, it won't run, because the JVM won't be able to find the packages you need. You can take your source code and you can try and compile it on JDK 9, and it won't compile, because the compiler won't find the packages it needs. What packages are affected by this, or what modules are affected by this? Well, there are 6 modules. Corba is the first of those. Anybody here using Corba? No. Good. Corba is one of those things that came 20 odd years ago and was popular for a while, and it got added to Java, and then nobody ever used it after. So it's sort of one of those things that's just been hanging around for ages and really needs to be got rid of. But then we have some other things as well. Java.transaction, that's also related to Corba, so we don't need to worry about that. Java.activation is part of the Beans framework. So if you've used Java Beans at all, and the Java Beans framework, then you may have to look at what code you've written. Then there's Java XML bind, which is the JAX-B, a Java API for XML binding. So you can take an object representation and convert it into XML, and from XML back into an object representation. So if you've used JAX-B, you may need to rewrite some code. And then the last 2 are related to web services. But these are SOAP-based web services rather than the much more common RESTful-based web services. Does anybody here still use SOAP-based web services? Ooh, this is a good audience. You have done very well. I often find that there are quite a few people who are still using SOAP-based web services, but that's not going to be a problem for you. So these are the things you need to consider in terms of changes. JDK 9 is starting a trend of not just adding features, but removing them as well. And that's a good thing because it's starting to tidy up the JDK. It's been overdue for quite a while. Things like Corba, we really don't need to be shipping those in 2018. We can leave those out quite happily. And there are some other things as well, which we'll talk about. So now let's talk about moving Java forward faster. This is something that was announced back in September last year, just before the Java 1 conference. And again, Oracle and the OpenJDK developers made some announcements about how JDK, OpenJDK, was going to be developed in the future. They announced that there is a new release model. The idea here is that there will now be a new release of Java every 6 months, twice a year in March and September. And we've already seen that this year, JDK 10 came out in March, which is why when I started talking about JDK 9, I said I was talking about history, because JDK 10 is the current release. JDK 11 will be coming out next month. It is actually next month now. So we've had 3 releases in the space of a year, having waited 3.5 years for the last release. This is a radical change. And there's a good reason for it, because we wanted the development of OpenJDK to be more agile. Rather than having to wait 3.5 years, or 3 years, or 4 years for a new release with new features, we need to get those features to developers more quickly. We need a more agile approach where we can look at the requirements, we can respond to those requirements, and get the features to the users in a much more timely manner. That's the way that we develop software nowadays. We use agile methodologies, we don't use the waterfall approach that we used to use in the past. So the OpenJDK developers had a goal of a release every 2 years, and they never matched that. They actually never managed to get a release out in 2 years. It was 3.5 years between JDK and JDK 9. The way this is going to work is by changing how features are added to Java. In the past, when the developers sat down and said, right, we're going to start JDK 6, they sat down and said, what features are we going to put in JDK 6? They made a list, and then they started working on it. And only when all those features were finished did they then ship JDK 6. That would often lead to delays. We saw that with JDK 9. The modularity system had to be changed a couple of times, and things needed to be reworked, so we had some delays in JDK 9. If we want to release every 6 months, we can't do that. Now, rather than having the features drive the delivery, it's the other way around. So we simply say every 6 months we will take whatever is ready and we'll put that in the next release. If something isn't ready, it gets delayed to the next release or another one after that, whenever it's ready. So we can much more easily hit the target of a release every 6 months. And as I said, we saw that work in JDK 10. JDK 11 is already in the ramp down phase 2, I believe it's now. Might still be 1, but I think it's 2. So they're very much on schedule for getting JDK 11 out next month. So this is all good. The fact that we get more features more quickly. However, we need to think carefully about how do we provide updates, how do we provide support for these new releases. And the thing about having a release every 6 months is it rapidly becomes unmanageable in terms of trying to update many older versions, because even if you look at the last sort of 3-4 years, you're talking about maybe 8 or even 10 versions that you need continually being updated. Oracle, when they announced the idea of a faster release cadence, also said that they were going to adopt the idea of a long-term support strategy. This is the same idea that people like Ubuntu use. Rather than every release having support for a long time, you say, let's pick one every, in this case, 3 years, and make that a long-term support release. People can use the intermediate ones and get the new features, but if they're more interested in having longer support for commercial applications, for enterprise applications, then they can use the LTS release. To get things started, JDK 8, which is what was at the point the current one that everybody's using, they said that's going to be an LTS release, so they continue to provide updates. And then the next one is JDK 11. So when we get JDK 11 next month, that's going to be an Oracle long-term support release. Oracle also decided that they were going to do some convergence in terms of binaries. How this is going to work is that traditionally we have the binaries for the JDK that we download from java.oracle.com, or as it used to be java.sun.com. And when you download that, you have to tick a little box which says that you accept the Oracle binary code license for Java SE. Now, I don't know about you, but I've never read the Oracle binary code license for Java SE, but I do know that it has a couple of restrictions. One of those is called the field of use restriction. That dates back to the times of Sun, and it says if you want to use the JDK and the JVM for free, you can do it as long as it's on a desktop or a server. If you want to put it into an embedded device or a single purpose machine like a kiosk, then you need to negotiate a contract to use that. So this is the typical way that we've been used to getting our JDK. Oracle are now providing a second binary. This is the OpenJDK binary. What they do there is they simply take the source code of the OpenJDK, they build it, and then they make that available as a separate binary. That's available through jdk.java.net, and rather than being under the binary code license, it's released under GPL v2 with class path exception. Less restrictive license in terms of where you can use it. There's no field of use restriction. The important thing about these binaries is that they will only get updates for 6 months until the next release comes out. So there are 2 scheduled releases between each 6-month release. Once those are done, then the OpenJDK binaries will not get any more updates. The other thing that's quite important is there's no overlap, because you stop getting updates when the next one comes out, rather than what we've been used to in the past of having a period of time where we can migrate to a new version of the JDK. There's no overlap. So once JDK 11 stops, or JDK 12 stops, JDK 13 starts, and that's it for how you get your JDK. Oracle also want to make the binaries that are created, the one that you get from OpenJDK source and the one that they build as the Oracle JDK, they want them to be the same. To do that, they're doing 2 things. So the first is that they have contributed some of the commercial features, or most of the commercial features, that used to be in the Oracle JDK to the OpenJDK project. Things like flight recorder, things like mission control, there's some other things like application class data sharing, have all been contributed, or will have been, by JDK 11 to the OpenJDK project. That means that when you build the source code, you can get flight recorder, you can get mission control, and you can use them for free, which is a change in the way things are being done. The goal, which is pretty much already done now, is that there will be no functional differences between the Oracle JDK binary, the one they provide on java.oracle.com, and one that you can build directly from the OpenJDK source. So this is quite a radical kind of change. So that we're just going to have one set of binaries, one effective functional set of binaries, and one set of source code. So that's going to be completed by JDK 11. Now, having explained all that to you, let's eliminate some confusion. I talked to a lot of developers about what's changing with Java, and I talked to a lot of customers, and I read Reddit, and I look at blogs and things like that. And people have seen all this information, and they've made some assumptions which are incorrect. So let's clear up a few things. in terms of what's happening with Java. First thing is Java is remaining free. So it's not that Java is going to be purely commercial in the future. Java is still very much free in the sense that you will have OpenJDK builds that you can get from Oracle, you can get from Azure, you can get them from other people as well. And because it's under the GPL v2 license, it is completely free. You do not have to pay anybody to use Java. You can carry on using Java 8, JDK 8. You can carry on using JDK 7, JDK 6, JDK 5, any of the early releases without having to pay at all. So you can carry on using them, they are still completely free. So that's not an issue. I have said there will be a long-term support release every 3 years. Great. What that doesn't mean, though, is that's 3 years of free updates. A lot of people think that because JDK 11 is a long-term support release, and there is a new long-term support release every 3 years, that they get 3 years of updates. No, you do not. Because another change that's happening with JDK 11 is Oracle are going to change the license for the Oracle JDK binary. They're changing it to say that you can still download it for free, you can still use it for development, you can still use it for demonstrations, you can still use it for those types of things. But if you want to deploy it into a commercial system, you will need a commercial support contract from Oracle to do that. From JDK 11, the only free binaries, as in free to use without commercial support contract, are going to be ones built from OpenJDK. So that's the ones from Oracle, the ones from Azure, and the ones from some other people as well, if they decide to make those. If you want to continue to use Java and you want free updates, then you are going to have to change your JDK every 6 months. There is no long-term support for free, but Java is still free. And you can change your JDK every 6 months when a new version comes out, and you will get 2 updates as public updates, and you'll get all the security fixes, all the bug fixes available without charge. But you're going to have to change every 6 months. For most people, that is quite a daunting prospect. Now, this has already started to happen because I installed Java on my laptop, and I got this message come up. Now, obviously, you probably can't read it at the back, but we highlight better that it says, changes are coming which will impact your access to future releases of Java SE from Oracle. Corporate users will be impacted as soon as January 2019. What this means is that JDK 8 is going to stop having public updates as of January next year. January 2019 is when updates to JDK 8 for commercial users stop. If you're running Java on your laptop or your PC at home, and you have a son like mine who plays Minecraft, then you will continue to get updates to JDK 8 for free until the end of 2020. So there's going to be an extension for non-commercial users. Now, Oracle have put this into a diagram so you can see how this works. Again, a bit of an eye chart test, but effectively the orange parts are the ones which are only for people with a support contract from Oracle. Things like JDK 6, JDK 7, they already stopped the public updates for those some time back. You could still get support for those if you wanted, but you needed a support contract. The same is going to happen with JDK 11. JDK 8, as I say, public updates stop for commercial users as of January next year, and non-commercial users will still get updates. And again, if I sort of zoom in on a couple of bits here, what we can see is that the orange bits, like I say, are only for Java SE Advanced customers. The green ones are the OpenJDK builds. So when we get to 11.02, the next one in terms of OpenJDK is JDK 12. So there's no long-term support for OpenJDK builds. If you want long-term support for JDK 11, it's going to be as a part of the Java SE Advanced package. So like I said, that's some of the significant changes that are happening in the way Java is delivered and updates. Let's talk a bit about the future of Java. Actually, no, this is still the same. This is still today, isn't it? Because JDK 10 is with us. So yes, let's continue talking about it today. What's in JDK 10? Well, the first and probably the biggest change in JDK 10 is the introduction of local variable type inference. Java finally gets the var, I was going to say keyword, but it's not a keyword, it's a reserved type. That's a very subtle distinction, but it is quite important. What you can now do is, rather than specifying the type of your variable, you can let the compiler infer it for you. A very simple example here is I can say var list equals new array list of type string. In that case, the compiler can very obviously infer that the variable list is an array list of type string. I could do the same thing and say var stream equals list.stream. And again, the compiler can infer that because list is an array list of type string, that the stream we get from that is going to be a stream of type string. These are very simple examples, and they obviously make it look like it's a nice, simple feature. There are a couple of things you can do which are a little bit more unusual. So you can do things like anonymous inner classes and use var to actually get a type which you can't represent in the standard Java syntax. You want to try and create a variable which has two interfaces. You can't actually do that, and it represents just two interfaces. You can't actually do that in normal Java, but you can do it with an anonymous inner class and var. So there's some interesting things you can do there. Oracle have provided some style guidelines for this, because it's a nice feature, but it's also one that you can use in the wrong way as well as the right way. And you can make it so that your code becomes less readable rather than more readable. So the appropriate use of variable names is a good idea. So things like var string list equals and then list. It's obvious that it's a list of strings. Var s or var l is not such a good idea. So there's things like that. Also, you need to be careful if you use the diamond operator, because in this case what we're doing is we're saying var item queue is a new priority queue, but we're not specifying the type of the generic parameter. We're leaving the compiler to infer that for us. But because we haven't given the compiler any hints, it's just going to assume that it's a priority queue of type object. So these are the little things that you need to be careful about when you're using local variable type inference. But there's lots of good places where you can use this. Other things going into JDK 10, there's a number of what are called JDK enhancement proposals, or JEPs. First of those is the idea of improving the performance of the G1 garbage collector, because people were complaining that compared to the parallel collector, it wasn't doing quite so well. It's good for, or it's better for low latency, but it's not quite so good in terms of performance compared to the parallel collector. So now G1 has a parallel phase for a full compacting garbage collection, so it actually performs a bit better than it did. Application class data sharing, I mentioned this was a commercial feature that's now being integrated into OpenJDK. This was something that allows you to share data amongst a group of JVMs so that you don't have to replicate it. If you've got several JVMs running the same application, you can actually share data between them in terms of classes and so on, without having to replicate it for every JVM. It's much more efficient in terms of resources. There is the inclusion of an experimental JIT compiler. We'll come back and talk about JIT compilers in a lot more detail later on. But Graal is a project that's been around for quite a while. It's a JIT compiler that's been written in Java, and it's designed to give you different performance characteristics, better performance characteristics than you get with the traditional way of doing things. Still experimental, still work going on it, but probably we'll see that at some point making it into the standard way of doing things. There's the addition of root certificates. This was something that was left out, or the file was empty in OpenJDK. The Oracle JDK had a set of root certificate authority certificates in it, and those have now been added to OpenJDK. And then a minor thing, they've consolidated some of the source code repos of the JDK itself from 8 repo trees into 1, and that just makes life easier for the developers. A few more things, heap allocation on alternate devices. This is the idea, which actually came from Intel, of being able to put your heap not just in RAM, but in non-volatile RAM. Because there are, well, there's non-volatile RAM from, funny enough, Intel, which now performs almost as well as normal DRAM. And that way you can put your heap on a non-volatile RAM. Some more cleaning up. The Java H tool, which is used for JNI, that's been removed, and now there's a -H option on Java C that does the same thing. Pretty minor interface. An internal garbage collector interface. This was proposed by Red Hat, and it's not about having an interface from an application to the garbage collector. It's about being able to replace the entire garbage collector in the JVM through a standard interface. That's good for Red Hat because they have the Shenandoah project. It's also good for Azul because we have C4, which I'll talk more about in a moment. And then last one that I've got here is thread local handshakes. This is a low-level feature in terms of the JVM itself and to improve performance because it allows you to execute callbacks on single threads without having to get to what's called a global safe point. A global safe point is where all threads have to find a point where they're all considered safe, and by doing that, it can actually slow things down. So this is the improvement in performance. There are 73 new APIs in JDK 10. Interestingly, there are no new classes. There are some new methods, but there are no new classes in JDK 10. Most of what they've done is around collections. So there's the ability to create a collection using a factory method so that you can do things like that. You can also do copy of in terms of collection, and that will create an unmodifiable or immutable collection for you. And similarly, for the Streams API, there are now some new collectors which will generate unmodifiable collections as output. And there's also an optional or else throw, which is exactly the same as get. So I don't know why they've actually just added this new method, which is longer than get, but they have. A few miscellaneous things in JDK 10. Apparently, the XML input factory new factory method was incorrectly deprecated in JDK 9. So they have now undeprecated or de-deprecated or precated that particular method, so now it's had the deprecated tag removed from it. More cleanup. They've removed the entire com.sun.security.auth package. Actually, no, not the entire thing. Actually, 6 classes were removed from that package. And the security manager in java.lang, that's had a deprecated field, and 7 methods removed from it. More importantly, the JVM is now more Docker aware. One of the problems we had with Java and Docker before was that when you started up the JVM, if you didn't specify things on the command line such as the heap size or the number of threads for the fork join pool, it would define those by default. And the way it did that was by looking at how much resources the underlying machine had. But what it did was it looked at the entire machine, not at the C group, which potentially that JVM was running in. So if you're running it in a container in a C group with only 2 cores and a gigabyte of memory, the JVM might have started up and said, oh look, this machine has 12 cores and it has 64 gigabytes of memory, and it would set things accordingly. And that could actually result in your JVM stopping abruptly because it tried to allocate more memory than it had the right to do, and it would just stop. That's all being fixed now, so it's C group aware and works quite happily inside a container. Right, now let's look at the future. JDK 11, future just around the corner. What are we getting in JDK 11? Well, there are 17 JEPs in total. I'm not going to go through all of them because we don't have enough time to do all of that. But interestingly, there are 3 more from outside of Oracle. And this has become a good trend. Started off with Azure. Azure was the first company to get a JEP into JDK 9. Then we saw that Intel and Red Hat got JEPs into JDK 10. Now in JDK 11, we've got a couple more from Red Hat. So there is the Epsilon garbage collector. The Epsilon garbage collector does not collect garbage, which is a kind of interesting idea for a garbage collector that doesn't do anything. The reality is that that's there to enable you to test other garbage collectors. So you can run your application with the Epsilon non-collecting garbage collector. As long as you don't run out of memory, you can see your performance level. Then you put your new garbage collector in and you do the same thing, and you see what the delta is between the two. You can see what the impact of your garbage collector is. Red Hat also done some things around the ARM architecture 64-bit processor, and they've added some interesting things there. And then, this is quite surprising, Google have got a JEP into JDK 11 around low overhead heap profiling. So some interesting things there. A couple of other things that are going in, probably the big one is the idea of dynamic class file constants, or as it's been nicknamed, CONDI. This is about improving the way the JVM works with languages other than Java. Because if you think about it, lots of people have written compilers like Kotlin, like Scala, JRuby, all those types of languages that can be compiled from those languages into bytecodes. The thing is that not all languages, funnily enough, are like Java, but the JVM was originally written to run Java. So we've seen that in JDK 7 we got the invoke dynamic bytecode, which was designed to help dynamically typed languages run on top of the JVM. The dynamic class file constants is another sort of step forward in terms of helping compiler writers and language designers to use the JVM efficiently when they generate bytecodes and run different languages on top of it. Flight Recorder is pretty much the last piece of merging or eliminating differences between the OpenJDK and the Oracle JDK, so that's in there as well. Other things, yes. So the Corba and Java EE modules, the ones which aren't compiled by default in JDK 9 or used by default by the JVM, they are now going to be gone as of JDK 11. So this is the nice thing about having a module system. By breaking things up, it's much easier to take out these old features and have them removed in a nice clean way. So that's happening with Corba and those other Java EE modules. The HTTP client module, which was introduced in JDK 9 as an incubator module. So it's the idea that you try it out, give feedback without making it part of the standard. That's now gone through enough of a testing phase. People are happy with it, so now it's been moved from an incubating module into a full, proper module in the JDK. And then another thing which has been introduced is extending the use of local variable syntax to Lambda expressions. This is so that now you can do something like this. You can do var x, var y is the parameters to the Lambda expression which does x process y. Now, when I first looked at this, I thought to myself, well, hang on, that makes no sense at all, because Lambda expressions already have type inference. So if you specify that without the var, it will do exactly the same thing. So var seems to add no value at all. However, there is one situation where it does prove to be useful, which is if you wanted to add an annotation to that Lambda expression parameter, you could do at I don't know, non-null var x, and something like that. So you could add an annotation. You couldn't do that before. So it's a small change which allows you to do that. Where do I go here? Oh yeah, some other sort of smaller weird things. So there's these things called curve 25519 and curve 448, which is part of the elliptic curve Diffie-Hellman algorithm set. And so there's key agreements for encryption that are using those. Aha, Unicode 10. I always like Unicode because this is kind of fun. So Unicode 10 is the update to the Unicode code set. And I looked at this, and it turns out that Unicode 10 adds 8,518 new characters. And you think to yourself, where did they find all these characters? And it turns out that lots of them are actually emojis. But they're also adding the Bitcoin symbol. So now this is very important, we have the Bitcoin symbol. And then there's things like Nishu and Suyombo and Zanabazar Square, which are, if I remember rightly, Nishu is a code set or font, character set, I should say, which is used by Chinese women to write poetry. Again, very important to have that in our Unicode code set. And then the other two are to do with Tibetan monks writing prayers or something. And then, oh, this is important, the long-awaited, apparently, Colbert emoji has been added to Unicode 10. So this is the kind of thing which is important to have in Java. Interestingly, because in JDK 9 they added Unicode support to property files, you can actually use emojis in your property files as well. Or the character set used by women to write poetry in Chinese. Some other APIs that are being added. Again, no new classes in JDK 11 that I spotted, but some new methods. Things like the ability to create a null input stream which returns nothing. Not totally sure of the use of that, anyway. Similarly, we can do the same thing on reverse. We can have a null writer, so you can throw as many characters at it as you like, and nothing's going to happen. And then path.of, which takes a set of strings as parts of a path and creates a path for you. Right, looking further into the future, what are the bigger projects which OpenJDK are looking at in terms of the future of Java? We've got lots of small things, lots of APIs and little bits here and there, but what are the bigger projects that they're working on? Well, there's a set of these, and I'll talk a little bit more in detail about some of these. So there's Project Amber, and that's about simplifying the syntax of the Java language. This is something that people often complain about with Java, which is how much boilerplate code is required to do simple things. And if you look at languages, Kotlin is a good example because they've simplified a lot of the things which people don't like in Java. So Amber's about trying to look at how they can change some of the syntax of Java, not radically, but do it in such a way that it reduces the amount of code you have to write by default. Valhalla has been around for a while, and this is the idea of value types. I'll explain what that really means in a moment. Project Loom is about how to improve the way that you can use threads in Java. If you want to have literally thousands or millions of threads in a Java application, how do you do it in an efficient way? Project Metropolis is the idea of rewriting the entire JVM in Java. I'll explain a bit more about that as well. And then Project Panama is a replacement for JNI. JNI has always been a bit complicated, so they're trying to make it simpler. I'm not going to bother going into more detail about that. Project Amber. A few things already made it into the JDK, so local variable type inference and the local type variable syntax for landers. These are both things we've already looked at, so those were part of Project Amber. But then there's some other things. So there is another change coming to landers. One of them is the idea of using a single underscore as a parameter in a lambda expression. In JDK 9, a single underscore. JDK 12 is raw string literals. This has always been something of an issue with Java, is how you represent strings. Because yes, you can represent a string as having double quotes and everything between that is your string. But of course we all know that if you want to put a double quote in your string, you have to put a backslash. If you want to put a backslash in your string, you have to have backslash. And there's other characters that need to be escaped in order to do that. And you end up with some complicated things. Plus, there's no ability to do multi-line strings. Raw string literals are about changing that. So now, rather than using double quotes, you can use a back quote, and then everything between that back quote and the next back quote is treated as a string. And that includes new lines, it includes any characters like backslash, because in this case that would just be treated as part of the string. Now I know obviously you're going to look at that and go, well, hang on, what do I do if I want to have a back quote in my string? Because surely that's going to confuse it. Do I have to put escape character in front of that? No, because the way that you actually use raw string literals is that you can use one or more back quotes to indicate the start of your string. So you can actually do something like this. You can have back quote, back quote, back quote, a string with a double back quote in it, back quote, back quote, back quote. And that will work. So this is the idea of string literals. Pattern matching. There's some interesting ideas here. And this is pattern matching more to do with the way that it works in terms of things like the switch statement. This is something that's very difficult to do. Well, you can't do it in a switch statement at the moment. If you want to switch on something, you can switch on a value. So you can switch on a particular variable. Or you can switch on a string, or you can switch on, so you can switch on an integer, sorry. You can switch on a string, or you can switch on enumeration. But you can't switch on a type. So the idea is that with the changes in terms of pattern matching, you will be able to switch on a type. It avoids having to do a very complicated if, else if, and use instance of to do this kind of thing. So now if you've got a variable and you want to determine what its type is and do something based on that type, you can simply do case integer I, case like b, and so on. And that, in this syntax, would work, and you'll be able to do a switch statement that does something based on its type, not its value. They are taking switch expressions a bit further. Again, this is the sort of thing that we end up with in Java. And it's probably a little bit hard to read at the back. But essentially what we're doing here is we're saying, I want to switch on a day as a string. And I want to get back from that the number of characters in the name of the day of the week. So what I end up with is switch on day, and I've got case Monday, case Friday, case Sunday, number of letters equals 6, break. Case Tuesday, number of letters 7, case Thursday, case Saturday, number of letters 8, so on and so forth. So we end up with a lot of code to do this. And what we're essentially doing here is returning a value, or setting a value based on those cases. So every time we do something in our case statement, it's assigning a value to number of letters. Wouldn't it be nice if we could have the switch statement actually return a value which we could assign to a variable? Now we can simplify things a lot. So we can simply say in this case, the number of letters is the result of the switch statement. So the switch statement is now returning something. We switch on day, as we did before. Now, rather than having to have a separate line for each value with a colon, we're also going to allow comma-separated lists. Man, it took 23 years to figure that out. And then we'll steal some of the syntax from the Lambda expression, and we'll say, in the case of Monday, Friday, or Sunday, then we'll return 6. Case of Tuesday 7, Thursday, Saturday 8, and so on. But we also need the ability not just to return a value, but in true Java style, we need to be able to throw an exception as well. So if we have something which isn't one of those days, then we need to throw a new illegal state exception which says, that's an invalid value. So again, nice simplification of some code, but not radical change to the syntax of Java. Valhalla. As I said, this is about value types. Right from the very beginning, Java is not a truly object-oriented language because we have primitives as well. We have int, we have float, we have byte, and so on. That is because when Java was developed, treating everything as an object wasn't good enough in terms of performance. So they put primitives in to give you better performance. So primitives gives you performance, objects gives you object orientation. So it gives you encapsulation, it gives you polymorphism, it gives you inheritance, and so on. We end up with a problem because we might want to use a primitive in a certain situation where we can't. So we can't do an array list of type int, because int's a primitive, it needs to be a type, and a primitive isn't a type. So we can't do array list of int. What we can do is an array list of the wrapper class integer, but that's very inefficient, because if we want to put ints into our array list, we have to box them. So we have to convert, we have to take the value, we have to create a new instance of an integer, call the constructor with the value, put it in there, add it to the list. When we want the result, we've got to take that object, we've got to call the method on, get the value out, assign it, and then we've got to garbage collect it. So it's very inefficient in terms of objects. So we need a better way of doing that. And that's what Project Valhalla is about. It's about the idea of value types, which is something which codes like a class, but works like a primitive. And what this essentially means is that if you think of an int, let's say we've got an int 3, you can create an object representation of that, which is a new integer which has the value 3 in it. If you then do that again, and you call new integer 3, you're going to get another object. But those two objects are identical. They're an integer object that contain 3. So why not have a situation where when you create, or you create an instance of that which is a value type, something that doesn't change. That way, if you then create another instance of an integer which has 3 in it, you just point at the one that you already have. And then you can share it, in effect, between all the different threads that are going to use it. That has to have certain things, obviously, about it, because you can't change the value of it. Because if you change the value of 3 to 4, everything that thinks is pointing at 3 is going to suddenly point at 4. So it works like a, codes like a class, works like a primitive. So it can have methods, it can have fields, it can implement interfaces, it can use encapsulation, and can be generic, but it can't be mutated. That's very important. It's a value type. And also you can't subclass it, because by subclassing it you could effectively find a way of changing its value. Project Loom. So this is, as I said, the idea of improving how Java can work with threads. Threads at the operating system level are too heavyweight, because there are situations where you want to have lots and lots of threads in a Java application. And trying to map each of those threads to a thread at the operating system level is just too much. What Loom is about is the idea of fibers. So if you think that you have a process, and you can have multiple threads that map to a single process, fibers is taking that one level up. So you can have multiple fibers that map to a single operating system thread. They're treated in the same way as a thread, so they have the same functionality, but they don't have a separate thread involved in them. They're shared between a thread, and it's the JVM that does the hard work of actually scheduling them and dealing with them. So it's in essence, it's adding continuations to Java. And for those of you who can remember green threads, way back in the day when Java had to implement threads at the JVM level on top of operating systems that didn't have threads. Project Metropolis, running Java on Java. The idea here is to rewrite the entire JVM in Java, which gets a bit confusing, because then you think to yourself, okay, so I rewrite the Java virtual machine in Java, but then don't I need a Java virtual machine to run my Java virtual machine, because it's Java. And then, because that Java virtual machine is written in Java, I need another Java, and then you end up with this sort of recursive nightmare. No. Remember that Java is just a syntax of a language. You can write it in Java. You don't have to compile it into bytecodes. You can compile it into native instructions, so you can do ahead-of-time compilation. This is what the Graal project, a lot of the Graal project is about, is rewriting JVM in Java. This has a whole host of values to it, so it makes it easier in terms of porting JVM to new platforms. It makes it easier to write code for the JVM, because many more people know how to write good Java code than C++ code. And there are some issues around performance that need to be explored. Last thing I'm going to mention, we've mentioned some things that we do at Azul, and that's Zulu Java. Basically, our Zulu Java is a free binary distribution of the OpenJDK. We simply take the OpenJDK source code and we build it. Then we run it through the TCK. So we guarantee that what we've created meets the requirements of the standard. We have older versions available, so we have JDK 6, 7, 8, 9, and 10, and we have quite wide platform support, so we have the typical 64-bit Windows, Mac, and Linux, but we also have 32-bit for Windows and Linux, and then for people who are interested in embedded, or possibly using ARM and data center, there's ARM 32 and 64-bit, and even PowerPC. As I say, you can download that free from our website. no restrictions on that. Okay, so that is pretty much an hour. I'm doing really well here. So we'll take a break here, and then we'll come back and we'll talk about building a better JVM.
10 minutes break?
10 minutes break, perfect.
So we're going to continue from 8.
Right, part 2, building a better JVM. As I said at the beginning, one of the things that you find with Java is that you're running on top of the Java virtual machine. And the Java virtual machine, whilst a very powerful and a very convenient and very useful thing to have, introduces a level of indirection. It introduces a layer between you and the operating system. Now, what I did was I put together what I call the performance graph of an ideal JVM. So what we've got here is a nice simple graph, where when you start up the JVM, your application runs at 100% of its possible performance on that JVM. And over time, that doesn't change at all. You get exactly 100% from right from the very beginning to right at the very end. I'm willing to bet that nobody here has seen a performance graph of their JVM like this. And that's because of the way that JVM works. What we typically see is something much more like this. When we start off, we have a class file that we load. And that class file contains the bytecodes that have been compiled from the Java code. In order for those bytecodes to be executed, the JVM has to convert them into the native instructions of the platform that it's running on. This is the whole write once, run anywhere, or write once, test everywhere mantra that has been with Java right from the very beginning. So we see that at the beginning, we have to interpret every bytecode as it's used. And every time it's used, we interpret it again. There's no clever stuff that's being done here. If you're in a loop and you're using the same set of bytecodes again and again, the JVM is going to interpret those bytecodes every single time. So the performance of doing that is not very good. And this is why when Java first came out, and that's literally all it did when it was running code, everybody said Java's slow. Compared to C and C++, Java's very, very slow. To get around that problem, the developers of Java came up with some useful ideas. Probably wasn't their idea originally, but they looked around and saw what other people had done. And they said, right, let's take those bytecodes, and when we figure that there's a loop that we're running a number of times, rather than interpreting the same bytecodes again and again and again, let's take that method or that loop and let's compile it into the native instructions for the platform it's running on. That way, we can run it faster. That's where the hotspot idea came from. Why it's called hotspot is because it found the hotspots in your code. So at that point, we run a JIT compiler, just-in-time compiler, on the bytecodes and convert it into native instructions. The thing about the way we do this to start with is we use a thing called the C1 compiler. It used to be called the client compiler. And the way that compiler works is it's designed to compile the code as quickly as possible, to get it running as native instructions as quickly as possible. But what it doesn't do is apply optimizations. It only does the most basic optimizations based on what it can get from the bytecodes. So we get a bit better performance, but we don't get a whole lot better performance. What we also do at this point is, let's go back to that. What we also do at this point is we profile. So as this bit of code is being used again and again and again, we can collect more information about how that code is actually working. And we'll talk a bit more about that as we talk about JIT compilation later on. So we compile it quickly, and then we profile it as it runs. And at that point, we can then recompile it. So we take a different compiler, which has lots more optimizations, the C2 JIT compiler, and it starts compiling it, recompiles it using these optimizations. But a lot of the optimizations that we use will start to give us better performance, but they may be wrong assumptions about how the code actually works. When we see the wrong assumptions, something happens, At that point, we actually have to throw away the code we compiled, and go back to interpreted mode, recompile it, reprofile it, and go back again. So that's called a de-optimization, and that happens as the application starts to figure out what's going on. Once we've done that for a while, we get to a nice steady state of optimization. So the application is running, it's been running for a few minutes, maybe half an hour, and we've got nice optimized code. We're at our sort of peak level of performance in terms of the application. However, we still see these dips in performance every once in a while. The reason for those is not to do with the JIT compilation, but it's to do with garbage collection. So garbage collection comes along and says, we need to do something to clean up, and it pauses the application threads, which stops them and then reduces performance. What we have with the JVM are some challenges from a computer science design point of view. The JVM is a managed runtime environment, and there's two things that it does which are very significant in terms of giving us a lot of power, but also affecting the way the performance of the application works. So the first of those is the garbage collector. Now, the garbage collector is really good because it takes away the responsibility of memory management from us as developers. It's not like in C where we have to do malloc, it's not like where we have to do free and we have to remember free, and in C++ we use new and then we have to free up objects, so we're responsible for memory management. Garbage collector tracks all of our use of objects, and then when we don't need them anymore, it can reclaim the space automatically. Problem with that is it is inherently non-deterministic. We can't predict when the garbage collector will run. We can probably make some guesses at it, but it's just not easy or possible to predict exactly when that's going to happen. And we also see long pause times potentially with applications. So everybody here has written some applications. Who here has seen a garbage collection pause time that maybe lasted a second? Anybody? Oh, okay, somebody at the front. Anybody seen a garbage collection pause time that lasted more than a second? Anybody? Oh, okay, good. A couple of people. Right, so a couple of people have seen doing it. I was talking to one customer that we had who had garbage collection pauses in a Java application that lasted for 1.5 days. and I was talking to them and I said, well, hang on, how do you even know that the virtual machine hasn't crashed? How do you even know that it isn't just like an infinite loop? And they said, oh, no, we monitor it with JMX and we can see that it's doing the garbage collection and we see that it's working. And then I said, well, okay, if that's the case, why don't you just stop the application and then restart it so it doesn't have to do the garbage collection? And they said, it would take longer to reload all the data that we have in that application than it does to run the garbage collection for a day and a half. So garbage collection can have a significant impact on performance. Hopefully never for you where it's 1.5 days. Then there's this idea of bytecodes, not machine code. And the key thing there is the fact that we can have different strategies about how we adaptively compile that code. So we can use the C1 JIT, we can use the C2 JIT, we can do interpreted mode. How that all works changes the speed of the warm-up of our application. So our application is not going to start up as fast as it can possibly. It's going to take time to get to that point. So what do we do with trying to solve these problems? Well, we created this thing called the Zing JVM. And the Zing JVM is essentially where we take the OpenJDK source code, exactly the same as we do in Zulu. This time we actually make some changes. But everything we do still passes all of the TCK tests. So make sure it is exactly Java. You can just use it as a drop-in replacement for any other JVM. There's nothing that it will do differently from an application point of view, coding-wise, than any other JVM. What we do is we take away all the garbage collectors. So there's no parallel collector, there's no G1 collector, there's no CMS collector, all of those are gone. And we replace it with C4. And I'm going to talk more about what C4 is and how it does, how it works. This also works in conjunction with a thing we call Zing system tools. Again, I'll explain that in a moment. And then what we've done more recently is to replace the C2 JIT compiler with a new one that we've written called Falcon. And then lastly, to look at how to alleviate the problem of warm-up, we've created a thing called Ready Now, which looks at how to fix the problem of going from an adaptive compilation through interpreting through C1 into C2. So let's start with the continuous concurrent compacting collector. Hence why it's called C4. And the important thing here is the words. It is continuous, so it runs all the time. It is concurrent. It runs at the same time as your application. It is compacting, so it doesn't just leave objects where they are, it actually compacts everything into the smallest possible space. And it's a garbage collector. This works with the Zing system tools. And what we did was we said, well, okay, so the JVM is very good at manipulating heap space and memory. But wouldn't it be even better if we looked at how the operating system works at a virtual memory level, and we actually tune that to work specifically for the JVM? Virtual memory system in Linux has been designed for a broad range of applications. So it's a general purpose virtual memory system. Sure, the JVM is a general purpose application, but it's a particular type of application. So what we've done is to change the way some of the virtual memory system works to work specifically with the JVM. What we can do is some clever things in terms of how we allocate pages of memory to the JVM. If you look at a normal JVM, what it'll do is when it's using the heap space and it needs a page of memory, it'll go to the operating system and say, give me a page. What it'll get back is whatever page the operating system decides to give it. Most likely, it won't be a page that's in cache. It'll be one that it gets from somewhere else, and it won't be in cache. What we do is we make sure that where we can, because we monitor all the pages that we have, we'll give you one that's already in cache. So you get better performance straight away in terms of using that. The other thing that we do is when we've finished with memory for a particular part of the JVM, if we've cleaned up part of the heap, we'll actually return those pages to the operating system. And that way, for other JVMs, if you're running multiple JVMs, again, you can get much better use of the memory in the system. And there's other things that we do, which is things that are called quick release, which I'm going to explain as we go through the algorithm itself. One thing about this is that because of the work we've done, it is only supported on Linux. Theoretically, we could do it on Windows, but we just don't have the engineering resources to do that, and we haven't had enough customers asking for it. So right now, we only need support Linux. The basics of C4. Well, like many other algorithms, not every other algorithm, the C4 uses generations in terms of the heap. And the idea here is that you divide the heap up into regions which are divided in terms of the lifetime of objects that are stored in there. If you've ever looked at how a garbage collector works, you'll find that there's what's called the young generation, where objects are first allocated, and then they get promoted from the young generation to the old generation once they've lived for a while. We do the same thing, so we have both a young and an old generation, but we use the same collector on both. Most algorithms use a different collector on the young generation to the old generation. We use the same collector on both. And really the reason for doing that is more about efficiency than for other reasons. And a very important thing about how this algorithm works is the use of a read barrier rather than a write barrier. Again, we'll explain more about that. So the algorithm that we use is quite similar in some ways to the CMS algorithm. So concurrent mark sweep, we have three phases, which is mark, relocate, and remap. Right, digging into a little bit more detail. Read barrier. This is what we call our loaded value barrier. And this is what allows us to have your application threads running at the same time as garbage collection. And that's why with Zing you won't see these long pauses of garbage collection, because we're doing the garbage collection as your application runs. You don't have to pause your threads in order to move things around and do work. We can do all of that as your application is running. So the way we do that is when you want to reference an object, you get the object header. And we look at that object header and we test to see whether we need to do something with it. And we do that by enforcing two rules on what we get back from the object header. The first is that if we're actually in the marking phase of the collector, we guarantee that when you get the object reference back, it will be marked, either by the garbage collector or by checking when you actually get access to that object. And then when we're in the when we're in the relocation and remapping phase, we guarantee that you will always get the right reference to the object in terms of where it is. If we're in the process of moving it, you may get delayed slightly because we actually have to move the object from one place to another, but you will always get the right reference so that you don't get corruption of data as we move objects around. This is what allows us to do these things concurrently. So we actually can concurrently mark, we can currently relocate objects. A lot of people say to me, well, okay, if you're intersecting every read to an object, doesn't that place an overhead in terms of performance? Because you're adding something to every single object read. And the answer is, well, yes, it does, but it's almost imperceptible. The way we do it is by using some bits in the object header. And we can do a test and jump on those bits. So we look at a bit, we say, is that bit set? If it isn't, we jump to a handler. If it is set, we just continue because it's already processed. Nice thing about that is that's literally 2 instructions. And if you look at how that gets sort of converted down into the micro operations of a modern Intel processor, it's literally 1 micro operation that it equates to. That's basically a 1 nanosecond overhead on every read. And you just won't notice that in terms of most, in fact, every application you can think of will not notice the performance impact. So we look at a diagram of how that works. What happens is that the virtual machine runs, and at some point the garbage collector decides that it needs to start doing some work. What happens at that point is the garbage collector creates a root set. And this is common to a lot of other garbage collection algorithms. A root set is simply all the objects that you can reference directly from your application code. That means we scan the registers, and we scan the static variables, and we scan the heap, looking for all the object references that you have. So anything that's in those places, clearly you're using. So we put that into a root set, and that's our initial set of valid objects. But clearly, those objects will refer to other objects, most likely will refer to other objects. So at that point, we need to go through and we need to track from each of the objects in our root set to all of the objects that those can reference, and then from those objects to other objects and so on. So that's the idea of creating a graph of objects of all the reachable objects. And the way we do that is to say, okay, have a garbage collection thread which marks an object because it's in the root set, and then follow the links from that object to other objects that it can reference and mark them. So we know that those are valid objects. Because the root set is just a set of objects, we can apply parallel threads to that. So we can do the work in parallel. There's no difficulty with dividing it up into multiple threads. That's all nice, and we can do that quite independently. But of course, your application is running at the same time, and your application may decide to reference an object. If it does, we're going to do this test and jump. We're going to look at the bit in the object, and we're going to say, is that object marked? And we go, no, it's not marked, so it needs to be marked. At that point, rather than saying, okay, now we'll give it to the garbage collector and we'll let the garbage collector do it, we say, because this is such a small thing to do, we'll let the application thread mark that object. So now the application's referenced that object, it's valid, it's been marked. But because that object will probably reference other objects, we don't want the application thread to then have to start tracing all of the references, because that potentially could be an unbounded time. So rather than doing it that way, we then say, okay, take that object and add it to the root set. So that way when the garbage collector comes down, it will then find that object and trace the objects from it. So we know that when the garbage collector finishes its work, all of the objects will be marked. But you can see how even when the application thread is running at the same time, if it references an object, it marks it and makes sure that any other objects it references are marked as well. Then we have to do relocation. And what we're doing here is figuring out how to copy objects around so that we can compact the objects into the smallest possible space. So we have 5 objects, A, B, C, D, E. And what we want to do is copy them into some free pages and compact them so they're all contiguous. To do that, we can clearly calculate values for where we want to position them. So A becomes A prime, B becomes B prime, and so on. That allows us to compact them. So this is the relocation phase. We calculate the addresses of where those things are going to be moved to. What we then do is we start moving those objects. Again, if your application is making changes at the same time, if we're in the process of moving an object, it may get blocked for a short space of time whilst we move an object. So we guarantee that, you know, if we're moving the object, we don't want it changed. But it's a small period of time to move one object. Objects tend to be very small, so it doesn't take very long. What we also do is we create a side table. And the side table is the mapping from where the object was to where the object is going to be. That way A becomes A prime, B becomes B prime, and so on. And all this information is held in this side table. The reason we put it in a side table is so that the objects that we have in the upper part here, A, B, C, D, E, this is where we can get clever with our memory management, because you've got 2 things here. You've got the virtual address space of your application, and then you've got the physical address space of the memory in your machine. And the virtual memory system will map between the 2. Any other normal memory system would say, well, because you've got things in those pages, we can't free those pages up. Because if you free the page up and somebody tried to reference that address, it would be a bad thing that you get a segmentation fault. But we know, because we write the JVM, that you can never reference A or B again. There just simply isn't any way. So we can actually steal the page. So so we take one page to do the remapping. So we need one free page of memory. Then we'll move our objects into ABC. Now we know that we've got the data in our new page. And that way A, B, and C can never be used again. So then we can steal the page from underneath A and B, and we can use that to compact D and E. We can move those objects at that point. So this is what's called hand-over-hand remapping. So we only need literally one free page of memory to garbage collect the entire heap, and that goes all the way up to 8 terabytes. So you could have an 8 terabyte heap and you only need one free page of memory, well actually one free page per thread, and you could garbage collect the entire 8 terabytes of heap space. So that's the idea of quick release and the remapping. Yeah, so we'll just do that again. Right. So then we need to remap. So this is where we need to say, okay, we've got this information, A to A prime, B to B prime. We need to update the references that are being used for this. So at this point, our garbage collection threads will go into the remapping part. And they'll say, okay, for the object header, we need to change the address of where the object is. So we'll take A and A prime, and then we'll look at the object reference for A, and we'll change it so that it's now got the correct value in it. And we'll set a bit in the object header to say that particular object has been remapped. Our application threads are running at the same time, and so we do the same thing. If our application tries to access an object, that object may have been relocated. But because the bit isn't set, we do our test and jump again, and we say, okay, so this hasn't had the bit set, which means it's a relocated object. We need to change the address reference so it points at the new place rather than the old. We go to the table, we get the information, we update the object header, and then we mark it to say that it has been updated. That way, when you get the object reference in your application, you always get the right place. If it hasn't been relocated, you get the old address. If it has been relocated, you get the new address, and that's guaranteed. Because it's the application thread itself which actually does the remapping in the case of that object which hasn't been dealt with by the garbage collector. So that's how we can do it completely concurrently. As I said, big heaps for Zing are not a problem. We scale all the way up from 1 gigabyte to 8 terabytes. And this is one of those places where people were having 1.5 day pauses, and we completely eliminated that. So we said, okay, we'll use our algorithm, and suddenly that 1.5 day pause just disappeared because they didn't need to do that anymore. Literally, you don't see any degradation in pause times based on how big your heap is. The nice thing about that is quite often what we see with people is that in order to avoid problems with longer pauses on the heap space, they run multiple JVMs to break up the work and keep the heaps reasonably small. That's not a good design because, of course, they're trying to process a large amount of data. Rather than breaking it up and doing it that way, you can have a single JVM that can process all of that data in one heap. One thing to say about this, though, is that although Zing can work with very big heaps, it doesn't need them. Like I say, it will go all the way from 1 gigabyte without any problem. Now, one thing that's always good is to understand how you can actually show this working. How do you measure whether the JVM is actually doing what it's supposed to do, what the impact that the JVM's having? So we created this little open source tool called JHiccup. And JHiccup is a really neat idea because it allows you to see, with a real application, what is the impact of the JVM and everything below it, so operating system, hardware, networking, whatever. What impact does everything below the application have on the application? And the way it does that is by adding a thread alongside your application. It doesn't need to actually interact with your application at all. All we do is we set another thread in the JVM running, and that thread will spend pretty much all of its time asleep. So it doesn't really affect what your application does. The way it works is when you start JHiccup, it creates this thread and it says, right, what time is it right now? And then it goes to sleep for 1 millisecond. When it wakes up, it looks at the system clock and it says, what is the difference between the time when I woke up and 1 millisecond after I went to sleep? So what's the difference between when I thought I should wake up and when I actually woke up? If, whilst your thread was asleep, you had a garbage collection pause, and that pause was 20 milliseconds, then the thread is going to wake up 20 milliseconds later than it thought it was going to wake up. So you can measure that. And because you've got nanosecond resolution timing on pretty much everybody's hardware now, you can go down to very fine levels of granularity on this. So it records all that information, and then what we do is we generate histograms from that so that you can plot in a nice graph what's actually going on with your application. And you end up with nice graphs like this. So what this shows is the same application. In this case, it's a Hazelcast caching system, which is running on a 2-node system with a 1 gigabyte heap. So it's quite a small heap. And on the left-hand side, we've got hotspot. On the right-hand side, we've got zip. What we see here is, in terms of hotspot, I realise it's a bit difficult to see at the back, but from the scale on the graph, you get quite a big peak at the beginning, which is about 240 milliseconds. And then it settles down and it's doing fairly continuous garbage collection around the 25 to 40 millisecond range. It's just doing that all the time. If you look at the Zing side of things, it's right down at the bottom. So it's dropped down to, I would guess that's probably around the 5 millisecond range, maybe sort of spiking at about 10 milliseconds. Normally what we do is we actually change the scale on the graph so we can see more detail, but it looks more impressive when you actually set them to be the same scale. And then the other thing at the bottom gives you the distribution of pause times by percentile. That's really useful if you've got a service level or a level of service level agreement that you need to keep to, and you've got to try and have your machine respond within 50 milliseconds, 99.99% of the time. It's very easy to see on that graph whether you can actually hit that target. With hotspot, obviously it sort of spikes up and goes way up in the upper percentiles, but because Zing is very flat, it's just very flat in terms of the percentiles as well. So that's a small heap. We do the same thing with a big heap. This is Cassandra. So this is Cassandra running on a 60 gigabyte heap. So again, a nice typical sort of workload. And we've got hotspot on the left, Zing on the right. This time we're seeing a slightly different profile, but we're saying, okay, we've got a really big spike there on the left as it starts up, and then it's settling down with some fairly regular pauses, which even I can't read on the slide, which looks like it's about, where are we? Yeah, so it's about 100 milliseconds pretty average, spiking at about over 500 milliseconds. So over half a second for pauses. And then if you look at Zing on the right, it just takes that out completely. So there's no spikes, it's right down the bottom, and again, you'd have to change the scale of the graph to actually see what was really going on. So that's the kind of thing that you could do just by changing the way the garbage collector works. Change it from a write barrier to a read barrier, allow the garbage collection to happen truly concurrently with your application. Right, let's talk about what we do in terms of JIT compilation. Now, JIT compilation is one of those things where people often think that if you could just take Java code and compile it into native code, like you do with C and C++, that it would solve all of your performance problems, and it would just run so much better. The problem is that just-in-time compilation can do a lot more in terms of improving performance. And there's really kind of two reasons for that. The first is that in a language like Java, where you can load classes dynamically at runtime, it's not dynamically typed, but you can load classes dynamically at runtime. If you try to do things like a very typical compilation optimization is method inlining. You can't do that in many cases with static compilation, because you can't say that at runtime a particular class won't have been reloaded with a different method. In a JIT compiler, because it's running at the same time as the code, you know exactly which classes are loaded at any point in time, so you know exactly what method to inline, and you can make better improvements in performance. The other thing is what are called speculative optimizations. And the idea of a speculative optimization is to look at what's happened so far in your code and then predict, based on that, what's going to happen in the future. And I'll give you an example of that in a moment. Problem is that sometimes, and we saw this in the graph at the beginning, sometimes these speculative optimizations turn out to be false. So at that point you have to go, okay, I've made a mistake, throw away the code, go back to interpreted mode, and recompile if you need to. So let's look at an example of how that might work. Here's a rather contrived example, but it's good because it shows what you can actually do with speculative optimization. Here we've got a method that computes a magnitude, and you pass in a value. What we say is, if the value is greater than or equal to 10, then we compute the bias based on the value. If it's less than 10, then we simply use a bias of 1. Then we return the logarithm base 10 of the bias plus 99. So it's like I said, it's a contrived piece of code, but it's a little bit, it's good to show an example. What we might find is that we run the application, we profile it, and a situation where you get a value of greater than or equal to 10 almost never happens. You know, it's a very unusual, almost like an error condition. So all of the time you're running this application, it goes through the part of the if statement which ends up with the bias being 1. Okay, the compiler can look at that and go, okay, well, if the bias is always going to be 1, because that's what we're always going through in terms of the branch, let's change the code around a bit and say, if the value is greater than or equal to 10, then we still have to have a situation where, okay, we've done something wrong and we need to recompile our code. So if it's greater than or equal to 10, we'll call this uncommon trap, which will go off use the JVM and say, this code is wrong now, throw it away, go back to interpretive mode, and so on. Otherwise, rather than calculating the math log 10 of 1 plus 99, you return 2, because log of 100 base 10 is 2. So that's where you can see that rather than having to do all these method calls and if statements, you can make it a lot simpler and say, okay, in that case, it's going to give you much better performance. That's a speculative optimization, because it relies on the code always going through that side of the branch rather than the other one. How did we go about improving JIT compilation? Well, because C1 doesn't optimize the code, it tries to do it as quickly as possible in terms of compilation. Obviously, the place to focus is C2, because that's where optimizations are applied. So, the problem with C2 is it is literally 20 years old this year. It was written in 1998 originally, and it is a horrible monolithic design. It is a bag of string, and it's very difficult to change it and modify it and see if you can improve it. So we decided, rather than trying to modify it, we would simply start from scratch. And we looked around and we said, okay, are there some other projects that might be useful to do that? And we found an open source project which was called LLVM. This used to stand for the low latency virtual machine, but it's gone away from that now and it's just called LLVM. Really, it's a compiler project, and it's a set of compiler research that's going on that's being backed by a lot of people who know a lot about compilers. So you've got people like Intel, you've got people like AMD, you've got people like NVIDIA, who understand all about the chip architectures. Then you've got people like Microsoft, you've got people like Sony, who understand about how the operating systems work. So lots of clever people adding stuff to this project. What we did was we said, okay, that's a good starting point, but it's designed for ahead of time compilation. We took the compiler code and then we integrated it into the JVM. So we had to integrate it with the garbage collector, we had to integrate it with the way the thread scheduling works within the JVM and do stuff like that. Having done that, we put our changes back into the open source project so other people could use it, because we're good open source people, and we ended up with a nice JIT compiler that was modular in its design, and we could do lots of interesting things with that. So let's have a quick look at a simple example of how this could work. So this is a simple piece of code which sums the values in an array. So it simply goes through a loop and says, go across the length of the loop and add things up. If you give that to a modern compiler, it's going to look at that and say, this could be applied in terms of vector operations. And if you look at things like the Intel processor, you'll find there's things like AVX, AVX2, AVX512, which are single instruction, multiple data operations that work on very wide registers. So you put lots of values in your register in one go, and then you add things all in one operation. So it's very efficient in terms of doing things in a single clock cycle. Modern compiler will look at that and go, yes, I can apply vector operations to that. Something like this, much harder, because in this case what we're saying is, okay, we've got two arrays, and we check that the length is the same. If they are, then we're going to add the values of the array together if the second one is even. So it's a more complex piece of code, not hugely complex, but it's doing something a little bit different. And what you'll find is, if you take that bit of code and you give it to a traditional JIT compiler, you'll get something like this. Now, don't worry about all the different things there, because it's micro operations. But essentially, if I draw some boxes around that, what you find is that there is a bit of loop unrolling going on here. And effectively, the loop is doing two operations for every iteration of the loop. So it's trying to optimize it by doing loop unrolling, but not by a huge amount. So you get two operations, two elements processed per iteration of the loop. If we give the same code to the Falcon JIT compiler, so same code, what we get is some more micro operations, which look like this. And I'm sure you probably can't see that they do look a little bit different. But if you, again, draw some boxes around that, what you'll find is that there's a repetition 4 times of 6 instructions. And the way that's working, because this is actually on a sort of Broadwell processor, so it's using AVX2, which is a 256-bit wide register. It's putting the ints into those. Then it's doing so it's unrolling it 4 times and using 256 bits each time. So you're getting 32 elements of your array processed for each iteration of the loop. So compare that to the other one, which was 2 elements per iteration. This will do 32 per iteration of the loop. So that's the kind of thing that really can improve performance. And there's lots of other things like that we're doing with Falcon to just add more and more things that will improve performance of your application. Last thing we can talk about is ready now. What we do to look at warm-up. So we've seen our diagram of the traditional JVM and how it warms up in terms of speed. And we call this the warm-up time. I'm sure you're used to the fact that as you start your application, it takes a little while to get to its optimum level of performance. How can we solve that problem? Well, a lot of people say, and I've heard people who explain this more, couldn't you just let the application run for a while, and then you take a snapshot of all the compiled code, and you put that in a file somewhere, and when you start your application up again, just reload all that code again, and off you go, because it's exactly the same as if you restarted it. Well, that's a really nice idea, but it just doesn't work in practice, because there's many reasons why it won't work. Some of it's to do with the data that's stored in the compiled code, but mostly it's to do with the way that the JVM itself is defined. And there's certain things you can and can't do when the JVM starts up. And because of the things you have to do, you can't simply reload a bunch of compiled code and make it carry on working. So what we do with Ready Now is slightly different. We actually record a profile. And the profile, it's just a text file, in fact. So you can look at it and you can see what's being recorded. It's very straightforward. It's 4 things. So we record all the classes that are loaded at that point in time when you record your profile. We also record all the classes that are initialized, because just loading a class doesn't necessarily initialize it. So we record loaded and initialized. We also record all the profiling data that's been recorded by the JVM up until that point. So that was what was used when the C1 code was being run, and then when the C2 compiler, or Falcon, recompiled it, it was the profiling information that was used in order to generate the optimized code. And we record the speculative optimizations that failed. So what didn't work when we tried to optimize further. The nice thing about this is you can gather data for this over a much longer time. You've got your application running, you leave it to run for a couple of minutes, you can take a profile. But you can also run it for a week. You make sure that absolutely everything's warmed up, all the code you need is there, all the things that are doing are working. And so you can really, with this kind of thing, you can minimize a lot of the de-optimizations that happen when the system starts up. What we then do is we essentially load all of the classes, initialize all the classes, and compile most of the code before you get to the main entry point of your application. So it may take a little bit, there may be a slight delay as it starts up in terms of actually getting to that compiled point, but when you actually start executing your code in main, you're almost at optimum level of performance. We were talking to a customer this afternoon, and they discovered the thing about Ready Now is the first transaction will be a little bit slower, but once you get to the second transaction, things really take off. But the first transaction can be a little bit, slower than the rest of them. And this is the sort of thing you see in terms of performance graph. The orange line is what you typically see without Ready Now, so you can see the up and down where it's compiling, optimizing, de-optimizing, and then getting to a steady state. The blue one is where we're using Ready Now, loading all the information, compile the code, and off you go. The thing that we've recently tried to, or are adding to this, is compile stashing. Now I told you that you couldn't simply take a record of all the compiled code, store it in a file, and then reload it. So what we decided to do is take all the compiled code, store it in a file, and then reload it. But it's a little bit more complicated than that. So what we do is we say, speculative optimizations are a really big source of optimization, and you can actually account for about half the improvement in performance through speculative optimizations. So what we do is we keep the compiled code for individual methods, and we put it in a file. But we don't just put the code for the method. We create what's almost like a fingerprint. So the fingerprint is the method signature, plus the compile code, and the profiling information that was used when that code was compiled. That way, when we want to try and reuse that code through the compiler, we can look at the fingerprint and say, does the code that was compiled for this particular method, using this set of profiling data, does it match what we've got that we're looking for? So we're essentially having a cache. So we can say, JVM compiler needs this method with this particular set of profiling data. If it's in the cache, we use it. Otherwise, we go to the JIT compiler and we say, right, recompile it based on that profiling data. What that gives us is a change to our graph. So now we've got our typical graph, and then we've got the Zine graph on top of that. So the idea of C4 is to eliminate these dips in performance once we've reached our steady state. So that's the garbage collection pauses, trying to eliminate those. Then we've got Falcon, which is saying, okay, let's lift the highest level of performance you get with your application to take it further up. And then you've got Ready Now, which is stretching that envelope out, eliminating as much as possible the warm-up phase, and minimizing the effect of that. So it's not quite the perfect graph. I mean, there will still be a few dips, and it does take a little bit of time to warm up, but it looks a lot more like the perfect graph than we get with a traditional JVM. To summarize, since I have literally a couple of minutes left, so talking about the first part of the presentation, Java continues to evolve. So we're seeing faster Java releases, release every 6 months, and the way that you get access to updates is something you do need to think about. That is changing, certainly changing as of September and then January next year. There are lots of good ideas to improve Java. Things like value types, things like fibers, things like Project Amber for syntax improvements and so on. And as I say, if you're interested in an alternative version of the OpenJDK binaries, then we can provide you with Zulu for free, and we'll even do commercial support at a very reasonable cost. And I have two of my colleagues here at the front who will be very happy to talk to you about the possibilities of providing that for you. End of commercial message. Better JVM, Zine. The idea here is to start fast, to go faster, and to stay fast. It is just a simple replacement for the JVM, so you don't have to recode anything, you don't have to modify the way things work. In fact, if anything, it's easier because you use less command line options than you would with other JVMs. And again, if you were interested in that, you can either talk to my colleagues, or you can try it for 30 days for free at azure.com/trial. And I will put the slides for this presentation up on SlideShare. I'll probably do it tomorrow now, and then they'll be available for you to have a look at. And with that, domo arigato. I hope I spelled that right.